Let's talk about finding least squares lines. This is also called linear regression. So here's the task. Suppose you're given some data in R2. So I've drawn a bunch of data points here in yellow. You want to find this line of best fit, this least squares line. I've drawn it here in blue, called it y equals beta naught plus beta 1x. And so the task is figuring out what are beta naught and beta 1. Well, what properties might we hope that beta naught and beta 1 satisfy? Well, if the line goes through the data point x1, y1, then we want beta naught plus beta 1, x1 to equal y1. If it goes to the point x2, y2, we want beta naught plus beta 1, x2 to equal y2. And so on for all of our data points. So this ends up giving us a linear system in n equations, where n is the number of data points, and in two unknowns, where the unknowns are the coefficients for the line, beta naught and beta 1. The problem is this linear system may be inconsistent. So in the example that I drew on the previous slide, the data points in yellow here and the blue line, what we'll see is the blue line does not go through all of the data points, which means there's not a beta naught and beta 1 that would work for all of these data points. So this linear system would be inconsistent in this example. Well, we don't want to just throw up our hands and say, if the linear system's inconsistent, we can't do anything. We want to find the line that's best in some sense. So let's go back and look at the linear system and see what we can do. So first, we'll write down this design matrix. So design matrix X. This is the coefficient matrix of that linear system. So the first column will be all ones, and the second column will be the x coordinates of the data points. We have this observation vector y. This is the vector of y coordinates for the data points. And we have this parameter vector beta, which is beta naught, beta 1. These are the unknowns that we're trying to solve for to find this line. And so the linear system we have is x times beta equals y. And even if this linear system is inconsistent, we can use least squares to find a solution. So remember, from a previous video, the least square solution for an inconsistent linear system is the best possible solution that we can get. It's not quite a solution, but it is the best that we can do. So in order to find a least square solution to x beta equals y, we solve the normal equation x transpose x times beta equals x transpose y. What does that mean for us computationally? We have to compute x transpose x. We have to compute x transpose y. We set up the augmented matrix, and we row reduce to solve. So let's take a look at a concrete example. Let's find the least squares line, y equals beta naught plus beta 1x, that best fits the data 1, 0, 2, 1, 4, 2, and 5, 3. So we set up our design matrix X. So the first column was all ones, and the second column is just the x coordinates of the data points, 1, 2, 4, 5. We have this observation vector y, given by the y coordinates of the data points, 0, 1, 2, 3. And we're trying to solve the normal equation, x transpose x times beta equals x transpose y. And we're going to solve it for the parameter vector beta. So we compute x transpose x, we compute x transpose y, we set up the linear system, and we row reduce to solve. So x transpose, remember, is the matrix whose rows are the columns of x. And so the first row of x transpose is 1, 1, 1, 1. The second row is 1, 2, 4, 5. So I can just take that matrix and multiply it by x. I do the arithmetic and I get 4, 12, 12, 46. So notice this matrix is symmetric. If you don't get a symmetric matrix when you compute matrix transpose times matrix, then go back and check. You should get a symmetric matrix. I compute x transpose y. And get this vector 6, 25. So we're trying to solve the normal equation, which looks like 4, 12, 12, 46 times beta equals 6, 25. So I set up the augmented matrix and I row reduce. First, I replace row 2 with row 2 minus 3 times row 1. It keeps row 1 the same and clears out one of those entries in row 2. Next, I replace row 1 with row 1 minus 12/10 row 2. So this keeps the second row the same and clears out an entry in row 1. And finally, I can scale row 1 and scale row 2. And then I have this in reduced echelon form. So I notice the solution, beta naught is negative 3/5 and beta 1 is 7/10. Which tells me the least squares line is negative 3/5 plus 7/10 x equals y. And so let's just plot this to make sure this is a reasonable answer. Right, so in blue, I've drawn in the original data points. Just to help with the plotting, I'll write everything out in decimals. Y equals negative 0.6 plus 0.7x. So the intercept is 0, negative 0.6. And I also plot this point 10, 6.4 and join it with a line. And what you'll notice is this red line that I've drawn here is a good fit to the original given data. In fact, it's the best fit in a least squares sense.